We're going to be talking about using QMCPACK for condensed matter as opposed to the molecular sort of calculations that we've heard about yesterday from Miguel. The key things that we're going to try to get out of this are how are calculations of solids or any condensed system, it doesn't have to be purely periodic, different from doing calculations on an isolated molecule. That's going to lead pretty quickly into what are finite size effects and how do we mitigate them in our calculations. And I'll also talk a little bit about current best practices for using pseudopotentials, which generally comes up in all of these. So the first preliminary is just how do we compute the interaction energy in a solid between the systems. So we're going to be using a finite size simulation to approximate an infinite solid, right? We're only going to have a few unit cells of our calculation, but we'd like to extrapolate to the properties in the thermodynamic limit of some piece of bulk. So obviously you can imagine doing calculations of ever larger clusters, and this converges really slowly, although for nanoscale sort of reasons it's quite interesting. What people do in pretty much all contexts is use some sort of periodic boundary conditions to speed this convergence. But when you move to periodic boundary conditions, the Coulomb potential between the charged particles gets replaced by an Ewald potential, so something that's periodic. So what do I mean by this? So this is the periodic interaction that's found by summing. So you've got two electrons, right? But now in periodic boundary conditions, if I want to take the interaction of one electron with its neighbor, I actually take the interaction of the electron with its neighbor and an infinite series of copies of that neighbor everywhere in the system. So it's a classical problem. It dates back a long way. Unfortunately, for the Coulomb interaction, it's only conditionally convergent. So you have to be very careful how you're going to evaluate this. So the standard procedure for this is to you say, okay, I can do some linear thing where I'm going to screen my Coulomb potential for a charged particle, and then have a negative screening. And so you end up with two sums. This is the interaction you're looking at. So interaction of two charges, one at R, one at R prime, and then all the periodic copies along my primitive translation vectors. And then I go to something that's sort of a screened version in real space that will decay quickly because I've got this exponential here since it's a Gaussian profile. And then I've got something in Fourier space that will also decay quickly. So I can sum both of these things. Now in QMCPACK, we do something a little bit better than this. So I told you we used, that the standard Ewald thing picks some Gaussian, and you can tune how wide this is. So something that was noticed a while ago, I think David's told me that this has been around far longer than the paper, is that instead of screening this delta function charge with a Gaussian, you realize that you've got plenty of freedom to screen it with whatever you like. And then you explore other choices of screening, right? And so you can actually optimize the form of this screening so as to minimize the number of turns that are going to be in your resulting summations. And you can get something that converges much faster. Now on a practical note, and it's a little bit hard to see, I guess, but the error in the method goes as it's an exponential of the cutoffs, the product of the cutoffs in real and reciprocal space. And this product is actually a parameter that goes into a QMCPACK calculation. Now, typically, we just set it to something that's relatively large and leave it. So you probably won't have to mess with this. But if you see the parameter LR dim cutoff, that's controlling how accurately we sum this infinite interaction of charged particles. So the next question is, why do we care so much to optimize this interaction? I mean, we're doing a fair amount of theory. The real space part of the Ewald sum has in the order of hundreds to thousands of terms, maybe. At worst, so does the reciprocal space. If you think back to the talk on Tuesday, we're getting into the era where calculations are free and data movement is not. So why do we really care? And then the question I have for you, now that you've done a few calculations, is, okay, over the course of a typical DMC calculation that you do, how many times are you going to have to evaluate the interaction between these charged particles? A typical simulation, we're going to have in the order of 100 electrons of something that we care about rather than the toy problems we've been doing, right? So we're going to do single particle moves where I propose to move an electron instead of all the electrons at once. And so each sweep through those, we're going to propose a move of about 100 electrons, right? For each one of these single particle moves, I have to calculate the interaction with all of the other 100 particles in the cell. In a solid state calculation, or most calculations, we have in the order of 1,000 walkers, and the population is generally moved sort of 1,000 times per simulation. So we're quickly up to 10 to the 10th evaluations of this interaction. So it's actually something that really makes a difference. If you change LRDIM cutoff in anything but the largest calculations that you do, you'll actually see that the walk clock time of your simulation will change by a reasonable amount. So also because we're paying particular attention to how these interactions are evaluated, it was fairly easy to put in arbitrary boundary conditions. So what I mean by this is purely periodic boundary conditions are sort of the norm in your plane wave, say DFT or whatever calculations, and that's sort of built into the basis set. We don't have to worry about that in Quantum Monte Carlo, right? You can put in whatever representation of your wave functions you want. Now all that we have to worry about is how you evaluate these interactions. So for instance, if you want to do graphing and you've got something that's periodic in 2 directions and open in the 3rd, and you don't want to be communicating with these images, you can just put that interaction into the code, and that's available right now. So it's actually a potential win in terms of efficiency that is not something we can generally say versus mean field methods. And then as we go through these slides, I'm going to have references, mainly so that you can download them later. But here, it's when you're looking on any issue involving solids, there's this review from 2001 that collects a lot of the older literature that's quite good, and I would recommend. And then here's the paper on the interaction. Okay, so the next thing that's a little bit different for solid state sorts of calculations versus molecular ones is the basis set for how we represent the wave function. So as we talked about before, the sort of simplest and most common wave function starting point for solid state calculations is a Slater-Jastrow form, right? We have some antisymmetric Slater determinant of orbitals of some kind, and then some piece for the dynamic correlation. So we're going to look at a Slater-Jastrow wave function at the moment. As we've talked about in previous examples, the Jastrow factor is something that we're just going to have to get through an optimization from the variational Monte Carlo. But it's the single particle orbitals that are calculated by another theory, typically. So whether this is some Hartree-Fock or DFT or whatever. So the most common source for single particle orbitals in a condensed matter calculation is going to be a DFT code. And typically we've favored plane wave DFT codes for this. So you've got some representation of each single particle orbital in terms of hundreds, thousands of plane waves, right? So if I want to move a particle from one point in real space to another in a plane wave representation, I have to actually evaluate all of these basis functions, which is really bad for Quantum Monte Carlo, right? So again, all in plane waves would have to be evaluated for every orbital. So what we do is we go to a real space representation, right? We've got a first quantized real space representation when we do the calculations. So we're going to just spline the plane wave function and then evaluate it in real space. So there's a lot of different choices for what splines that you could use to do this. 3D B-splines have found to be a good choice. So this is sort of an example of what the 3D B-spline basis looks like. So for any point in real space, you've only got 64 non-zero basis elements that you potentially have to evaluate. And it's very easy. So these are some sort of polynomials in x, y, and z. It's very easy to get all of our derivatives and Laplacians and gradients that we need for the QMC method. And it's also handy, although not necessary, that there are efficient routines to convert from your plane wave representation via an FFT to a real space that you can then fit to the splines. So it's quite quick to do this. Now the downside of the B-spline representation is that you're using a regularly spaced grid of points to calculate them. So what's good about this is that it's extremely efficient to look up in memory. If I want to evaluate all the single particle orbitals for a given location, I just store the array of data so that for a given location I get all the numbers at once. I hit my cache really nicely. I don't have to worry about stalling. The bad thing is that it can be quite inefficient in terms of total memory used. So imagine the case where all the wave functions might be small in a region of space. So if I do a slab calculation, let's say, I'm still going to represent with the same efficiency, with the same resolution, all the zeros in that vacuum if I don't do something clever. Another issue is that wave functions typically vary more strongly, let's say, near nuclei, right? So if you have a uniform spacing of these real space points, you're, again, going to be wasting in the interstitials compared to near the nucleus. And, right, so you can imagine also the case of like a Wannier function, where band 1 may be really large in the region of this atom and 0 out here, and vice versa. Because we've chosen a single grid for all of our wave functions, this is what gives us the nice property of striding through memory for all the orbitals at once, but it does have the downside that you could be storing a lot of zeros again. And I guess I should say that in practice, particularly on an architecture like Blue Gene, it's actually the memory that gets you, if you're not purely periodic, far before the cost of doing the calculations. So if I want to do some disordered liquid of a heavier element, like I've done calculations on xenon, the memory that you need to store the wave function actually is what stops you from going to larger systems. So QMCPACK does have ways to address a lot of these memory issues. So for instance, I mentioned the case of vacuum. So if I'm going to use plane waves to represent a molecule or a surface or something like this, we've got a thing in the code where you can use a coarse table that's valid everywhere. So I basically set the spacing really large. And then I say, OK, it's only near my atoms where I'm going to need a fine table that accurately resolves the features of the wave function. Typically do this by factors of 2. So it preserves the efficient streaming of data to the CPU. So it's very efficient computationally. However, you can gain factors of 2 pretty easily, factor of 8 maybe, but that's kind of the limit. So a next thing that's in the code but isn't widely used is this case where you might need a high plane wave cutoff or a large amount of resolution near an atom, right? So imagine you're trying to represent the d electrons that are localized. Now what you can do is do sort of either your real space mesh that the B-splines constitute, or around each nucleus, I can switch representation. So I basically say if I go close enough to a nucleus, I'm going to do some radial function times a spherical harmonic, which will be a much more efficient basis for this sort of thing, since they tend to only have a few angular momentum channels. Again, this preserves the property that my tables are very easy to look up. I know where I am in the table, and I evaluate all the orbitals from the same place in memory. So it's nice in that way. The memory used is often reduced sort of by a factor of 4 to 8 when you do this. The problem right now is that the conversion is a little bit painful and the tools aren't really great. So one capability that we don't have at the moment is the ability to actually localize the wave functions. So there was a paper that came out in PRL in 2001, where they basically said if you can localize the wave functions strictly in real space, like some sort of Wannier representation, and cut them off to 0. So really this only works perfectly, I think, in an insulator. Then you have the property that the number of wave functions you have to evaluate is kind of a local property rather than a global property of the system. So you can actually gain a factor of n in complexity there. Right. And this is something that some other codes do and that we've looked at, but the crossover to where the losing the nice streaming through memory is worth the increase in complexity seems to be for pretty large systems. So another thing that we use all the time is in the case of a highly symmetric system. So I'm imagining I want to do bulk silicon, right? So you've got some primitive cell that's 1 or 2 atoms, and then this is just going to tile everywhere in space. Now, if you were to try to represent the supercell of this, you would have memory that's going as n squared, right? Because basically you have to have n more basis functions for the increase in space, and then you've got n more electrons. However, if you use Bloch's theorem, you can actually construct wave functions in the supercell from different k points of the wave function in the primitive cell. And this is something, there'll be a little more details on this in the lab, but you get a factor of n, where n is the number of copies of the primitive cell. So if you're doing a periodic solid, we can actually go quite large and not worry about memory. So the last thing to talk about is actually just a computer science thing that QMCPACK does. So QMCPACK is a hybrid MPI and OpenMP code. And where this comes in is that, so the moves for a given walker, each walker is typically handled by a given processing element in a given generation, right? However, modern supercomputers typically have tens of cores per node, and the single particle wave function doesn't really change. So using a parallelization scheme that knows what's local to the node and what's non-local, it's very easy to share data like this between all of the cores on a node. So this is a sort of cartoon of what's going on, and that imagine this is the memory for a node, and I'm storing the walkers local to a given core on it, and then the big ensemble data is stored in the main memory. So you get kind of a factor of, say, 16 in a typical architecture, more memory for storing the wave function this way. And here are the references here. So just to see if everyone's still awake, does anyone want to answer, if I'm just using 3D B-splines, not doing any of these tricks, how does the memory usage increase when I'm doubling the system size for storing the wave function? Okay, so I've got a 3D grid, right? If I double the wave function, I'm going to have, assuming I keep the spacing constant, I'm going to have twice as many grid points. I've also doubled the number of electrons, so I've got to store twice as many orbitals, so the memory will go up as a factor of 4 if you double the system.
You mean the dimensions? Wouldn't that go by 8?
Yeah, that's what I...
Oh, it depends on what you mean by doubling.
8 squared.
Right, so if I'm doubling the dimension in each direction, then it would go as 8 squared. If I'm just taking 2 copies, it'll go as a factor of 2. All right, so the next thing about doing calculations of a solid or any periodic system is we're going to have finite size effects. So what do I mean here? So if we have periodic boundary conditions, that means that the Hamiltonian isn't changing when I have a discrete translation of my system, right, in multiple dimensions. And that means that you can imagine that single particle wave functions can get an arbitrary phase at the boundary. It's one way of looking at Bloch's theorem. So in order to get the thermodynamic limit, I really want to average over all these potential phases that I can get. So this is analogous to integrating over the Brillouin zone in density functional theory. And I'll describe a method called twist averaging that's a similar thing in diffusion Monte Carlo. So this really refers to averaging over the boundary conditions in the simulation. So I'm going to be talking about canonical twist averaging. You can actually imagine changing the number of electrons as you change the boundary conditions as well. If you choose to pick up a phase as you move across the simulation cell, it's actually an equivalent problem to adding a magnetic field, right? So you change your Hamiltonian like this. Now we can split everything into real and imaginary parts, very trivially. Now the problem is we're going to have fermions in our calculations. So we're going to have to apply something like a fixed node approximation. It's pretty easy to do that. Imagine where the wave function goes to 0 when everything's purely real. Something complex, it's a little more difficult. So you've got an imaginary part of the wave function. So there's a method called the fixed phase approximation that basically uses a choice for the phase as something you put in, and then you solve the real part of the equations in what looks like fixed node diffusion Monte Carlo. So in practice, there seems to be a fairly strong relation between the one-body finite size effects in diffusion Monte Carlo, which is what you'll be integrating over when you integrate over twists, and the integration over k-points in density functional theory. And basically, if they're predicting the same sort of Fermi surface and Fermi liquid parameters, you can kind of justify why this would be the case. For simple systems where the DFT is already doing a fairly good job, a kind of back of the envelope thing that you can do to correct for these one-body finite size effects rather than twist average is just do the DFT with the number of k-points that would correspond to your supercell, and then do the fully converged calculation and take the difference. However, diffusion Monte Carlo calculations for the different twist angles are actually statistically independent, right? You're just doing another number of calculations. So there's not a great cost in twist averaging in diffusion Monte Carlo. You basically split your population of walkers into a bunch of different populations, propagate them forward, but I still need n samples for a given error bar, right? So n propagations of the walker. The catch can come in that you have to equilibrate all of these calculations, and that's not linear. So in practice, there's a trick that you can do if you choose specific twists to keep the wave functions real. So it avoids having to do complex arithmetic in large parts of your code, and it's theoretically a little simpler. But then you only have sort of 1 to 8 twists in your calculation. And typically this isn't enough. So I'm showing an example here, although I guess it's a little bit faint, of the convergence for BCC beryllium with the number of twists that I'm doing. And you can see you've got a fairly large error here. This is Hartree in going from sort of 3 cubed to 4 cubed. Now often symmetry can be used, especially in these periodic solids that I've done a lot of calculations of, to reduce the number of calculations, which is handy. Now a more difficult problem is handling the two-body finite size effects. So you've got this thing that's analogous to what goes on in a mean field calculation on integrating over the Brillouin zone. But we also have this issue that we're evaluating an interaction that's periodic, right? So basically, if one electron is here and I'm calculating the interaction with another electron in the cell, it's actually an interaction with a periodic array, like I was mentioning before. But that implies some structure to, let's say, your pair correlation function that really shouldn't be there. And that introduces a finite size effect. Now for supercells of the same aspect ratio, so if I double all the dimensions, let's say, of the primitive translation vectors, the error in the energy, the finite size error in the energy per particle goes as 1 over the number of particles in the system. So one thing that people have done is you just do an extrapolation, right? So you do 3 different calculations, let's say, of different supercells, and then you fit this to a 1 over n. However, the cost of doing these calculations scales as n cubed, typically, right? So the most trivial thing that you can imagine doing, sort of 1 copy of the cell, 8 copies, and 27, is going to be massively more expensive than if you had a method of directly calculating the finite size effect. So there are several different schemes where I can do a smaller simulation cell and try to calculate what the effects of these spurious correlations will be. At the moment, all of these only correct for total energies. So it's something to keep in mind. If you wanted to calculate something other than that, basically you're stuck with doing a calculation in a large cell. So there are 3 methods that are in wide use. I'll go through each of them. One is to construct an approximate density functional that'll build in some of the information about the correlations. The other is to replace this Coulomb interaction, this Ewald sum, with something else that will hopefully have fewer finite size effects. And then the other is to look at the long-range behavior and say, oh, I know how to do long-range behavior in the random phase approximation. So I can fit my calculation onto that. So firstly is the use of an approximate functional. So this is a paper that came out in 2008. And they noticed that the widely used DFT functionals that we have for solid-state calculations, like LDA or any of the GGAs pretty much, are fit to correlations from the electron gas that were calculated with Quantum Monte Carlo and then extrapolated to the thermodynamic limit. So they've already taken care of these long-range correlations, right? However, there's nothing to say that you can't create a class of density functionals with a finite number of electrons where I keep these spurious long-range correlations. And so what they did is they did a lot of calculations of the electron gas with different numbers of electrons, fit a new analog of the local density approximation that had the finite size effects in it. And now what you do if you want to estimate the two-body finite size effects is you do one calculation with your typical LDA. You do another calculation that corresponds to the size of system that you're working with, and then you take the difference. So the best chance for this working really well is when the DFT is already doing a good job. So if you imagine the case where the DFT is predicting a metal instead of an insulator or something, you would imagine that the finite size effects for this sort of extrapolation might not be quite what you would see. And unfortunately, calculations or places where DFT is doing a good job is probably not where you want to spend millions of CPU hours on doing diffusion Monte Carlo. The next method of estimating these finite size effects is to do an effective interaction other than Ewald that hopefully will take out a lot of the finite size effects. So what's done is you try to create an interaction that has the Hartree energy calculated exactly, but the exchange correlation energy is evaluated just using 1 over r. So I'm not summing over all of the periodic images. And so the form of this is here. You basically need to know the density, right, from your DFT calculation, let's say, that I can use in a Poisson solver and get the Hartree energy. And then you're going to do some summation over the difference of that and the correlation energy. So it requires knowledge of the charge density, which you usually get from something like density functional theory. So again, you have to get a pretty good charge density from DFT, which is often not too bad. An added benefit of this is that the interaction here, because we're doing the Hartree energy exactly, and a lot of the correlation is coming from something that isn't infinitely periodic, is that the cost doesn't grow with system size, right? So it's actually a way to do the calculations of the interaction that scales more favorably. It can be quite accurate. The one big knock on it, as far as I can see, is that it only deals with the potential energy part of the correlation. So if you think to your sort of DFT decomposition, there's also a piece in the exchange correlation that comes from moving from non-interacting kinetic energy to interacting kinetic energy, and that's going to be missing. Now the other scheme is what I was mentioning, fitting to the random phase approximation. So basically you can write the interaction, the electron-electron interaction in terms of the structure factor of the system, but in a finite simulation cell, we're only getting certain samplings of the structure factor, right? Only those k points that are commensurate with my simulation cell will I see. So the finite size error, in one way of thinking of this, comes from the fact that I'm approximating an integral with a sum, right? And this sum isn't going to be particularly well resolved near k equals 0. So this is the long wavelength limit. So the dominant error in doing this, again, comes from k goes to 0. So what you can do is you can fit the calculated structure factor that you get from your calculation to an RPA form. So you basically need to get the plasma frequency. And then the correction is due to the difference between this integral. Similarly, you can write down an interaction for something for the kinetic energy that does the same thing, right? Where here I'm looking at the Jastrow factor. So what happens when the particles go to large distances from one another. Now, there's a sort of assumption here, if I'm going to be fitting to my calculated Jastrow factor and structure factor with a finite size calculation, in that I have to assume that that's not changing overly much when I do this in a small simulation cell. So if the finite size effects are actually changing where the particles are relative to one another, that would be bad. And here is from the paper in 2006 where they showed for silicon and they showed for the electron gas and a couple other systems that for reasonable size simulation cells, so here's a 32 atom repeat of silicon, there's almost no difference between where the structure factor is, just the resolution of where it's calculated.
You make it sound like this is something to do with RPA, but what we're doing is trying to find finite size effects that are related to correlation functions that you can measure in the QMC.
Sure.
So this is like what you do classically when you do finite size effects. You try to look at correlation functions that you can calculate, and within the calculation you estimate the finite size effects. It's not really, RPA just, these are exact sum rules for any system. It's not really an approximation, right? I mean, you
sure.
can show that these are, RPA is the simplest way to calculate them, but these are exact sum rules.
When I think in practice, RPA, so did everyone hear what David was saying there? So basically he was just saying that the way I presented it, it makes it sound like this is really based on the RPA. But what it really is you're calculating correlation functions that you can measure directly and then using relations to things like...
The other two things are based on density functional theory. So if you're doing the calculations to get beyond density functional theory, you kind of worry about using density functional theory to correct
yes.
results, right? I
Yeah.
think you said that, but yeah.
So, and in fact, the way that the RPA comes in is generally just that you kind of know a nice functional form that you can use.
Yeah, there are other ways around it that we have. We're supposedly going to write a long paper on this, but there are other procedures that do the fitting in different ways that don't depend on our particular functional form.
All right, so question for you then. How do finite size effects in Monte Carlo calculations differ from the finite size effects in a mean field method like density functional theory? Yeah.
Well, in QMC, you've got body finite size effects, which could predict that accuracy.
Right. So that's the primary difference, is that you have these correlation effects because of the interaction that you don't have in a mean field method. All right, so now I'll talk a little bit about something that's not strictly solid state or condensed matter related, but it is very important in practice in doing the calculations, is the use of pseudopotentials. The cost of DMC calculations scales kind of as n cubed. So generally, the wave functions that we use, like a Slater determinant, costs about n to the third to evaluate with a number of electrons. But the scaling with the charge of the ions is considerably worse. So it's estimated to be kind of z to the 5 to z to the 6.5. And so you've got a factor of n to the third due to the fact that I'm increasing the number of electrons. So it's the same scaling. Then the energy scale is increasing as z gets larger, right? The 1s electron is more strongly bound, so I'm resolving a much larger energy. And any error that I have there is going to contribute a lot of variance. And also our wave functions are typically not as good, so the time step has to be reduced. So we really want to avoid, in almost all cases, doing all electron calculations because of the expense. Needless to say that simulating chemically inert electrons shouldn't really change anything. So the obvious solution is to do what people have been doing in electronic structure codes for a long time, which is to introduce some sort of pseudopotential. And by this we mean, rather than having the 1s electrons there, you put in some effective interaction that's supposed to mimic what the 1s electrons do. And then you only simulate what's in the valence. So in most theories, this is a non-local object. So for the S symmetry around the wave function, you've got one potential for P. Basically, you're having to orthogonalize to the P electrons that you're taking out of the problem, so you have a different potential, and so on and so forth. All of the interactions that we've talked about in DMC so far have been local. So how do we introduce a non-local potential? So the first approach that we use is called the locality approximation. So this has been around for some time. And for a given non-local potential, what we do is we calculate our trial wave function. And then we basically evaluate this non-local potential using the trial wave function. So if you knew the wave function of the system, this would be an exact method. However, we don't. And then another thing comes in that this isn't a variational method. We often rely on the fact that if you improve the wave function in your DMC calculation, that you should get a lower energy and that you'll know that you're doing better. Now, strictly speaking, if you have a large non-local component to your pseudopotential, you might not know this anymore. It's possible that the locality error could actually bias your energy downward, even though you're doing more poorly in actually calculating the properties of the system. Right, so it's only applied to the non-local parts of the potential, and it's treated in a semi-local form. So I'll say a little bit more about that. So the pseudopotentials that we actually handle are a semi-local pseudopotential. So basically you have to project out the part of the wave function that you think is in the different angular momentum states around a given atom. Now, modern forms of the potential in DFT codes typically involve a projector. So basically you calculate the overlap of your wave function with some projector that sits on the atom. And this gives you an increase in complexity because basically you only have to do a local calculation in a sense. Now, unfortunately in DMC, it's not really tractable at the moment to calculate projectors. So everything that we're doing is semi-local. So also this means that a technique like nonlinear core correction isn't possible to use. Now, where this comes in and is a concern in practice is that we're going to generate trial wave functions with these Kleinman-Bylander, let's say, pseudopotentials, and then we're going to evaluate the DMC with a semilocal form. So in the case that, for instance, you have a large non-local channel, this can actually be quite a large difference. So now the fact that our DFT orbitals are well matched to our pseudopotential isn't necessarily a given. So all of this is basically to say, avoid as much as possible having a large non-local channel in your pseudopotential if you can. So there's another method for evaluating non-local potentials in diffusion Monte Carlo, and this restores the variational principle. So it was in 2006 it came out. So basically you introduce a discrete version of the Green's function. So you basically construct a lattice model around the atom, and then you use lattice techniques to sample this with the fixed node approximation. You'll see it colloquially referred to as T-moves, and it also happens to be somewhat more numerically stable. So sometimes you do a calculation in DMC with a pseudopotential that has a large non-local piece. You'll basically have some weird interaction with the nodes as you're evaluating it, and you'll see your local energy gets a huge spike. This technique gets rid of this. The downside has been that it's observed to have a somewhat larger time step error. So when you're doing your time step extrapolations, often if you're using T-moves, you'll find that you have to go to a smaller time step to get something that's converged. So far I've talked basically about mechanics. So given a potential, a pseudopotential, how am I going to do the calculation in diffusion Monte Carlo? I haven't really talked so much about what makes a good pseudopotential to use in Monte Carlo. So there's a paper from 1994 that actually establishes in a many-body sense what a good pseudopotential is. And basically you're looking at the density matrices and you find the natural orbitals of that, and you say if the natural orbitals are the same outside the core region for your pseudopotential and for your all-electron calculation, then you're likely to be doing well. Now in practice, people haven't often used this metric in constructing pseudopotentials. So most of the pseudopotentials that we use don't come from correlated calculations. They'll either come from Hartree-Fock or some sort of density functional theory. The exception to this is some of the quantum chemistry potentials. Now it's important to have a smooth behavior of the potential at the origin. Basically, if you've got some kink there, then you're going to have to cancel that out, or else you'll have a big spike in your local energy that's going to make things numerically difficult. A difference between, say, a DFT pseudopotential and a quantum Monte Carlo one is that we don't have to worry particularly much about how hard the potentials are. A large plane wave cutoff isn't really a problem, except that we're going to need more memory to store the wave function, but the cost is going to be just the same as for a soft pseudopotential. The thing that you have to be careful about is that a potential with a smaller non-local component will result in less error. So if your potential is hard, it may be that you have a large non-local component. And then I've mentioned this before, that in solid-state DFT codes, you're almost always using a Kleinman-Bylander form of the pseudopotential, but we use a semilocal form in evaluating the potential in diffusion Monte Carlo. So you want to be careful there. Does anyone have any questions on pseudopotentials in diffusion Monte Carlo?
Yeah, well, I have a little comment. The pseudopotential can be hard, but the difference between the different channels has to be small.
Yes. Yeah, so a great example of this is a Coulomb potential, right? There's no problem in doing a bare Coulomb interaction in diffusion Monte Carlo, and there's no non-local piece, so it's exact. So we've seen in the labs some ways that you can test a given pseudopotential that you're given. Does anyone remember some of the calculations that you can do to try to see how well a pseudopotential will perform in Monte Carlo? So those are two good ones to calculate. The one catch is that we're typically not doing a mini-body, or we're typically doing a single Slater-Jastrow calculation. So there'll be some error inherent in your choice of wave function. But if you can get within an EV, a tenth of an EV or so, you're generally doing quite well. Also calculating small molecules where you can compare it to experiment, something like a binding curve, is a good calculation to perform to test. So I have just a few miscellaneous points, and then I'll move on to more practical calculations that I've done. So I don't know if we need to wait on the coffee, but we might think about having the coffee break a little early this time. So the big question is, so I've got a trial wave function by calculating some Slater determinant of orbitals from DFT or some method like this, and I've put on some Jastrow factor. I've got a fixed node error that's coming from some other method, and I'd like to be able to reduce it. So the question is, how can we do this in the solid state? So we saw in quantum chemistry that I can do multi-determinant expansions, for instance, and then optimize over determinants. In plane waves, it's generally not feasible to do this. So the problem is that multi-determinant expansions in plane waves, in a periodic system converge very slowly, and for a given level of excitations that you're considering, they aren't size consistent. So to do very well, you probably have to have many, many, many determinants, and this is hard to keep up with. You might also like to directly optimize the single particle orbitals in Monte Carlo, right? Now, if you've used some sort of quantum chemistry basis to represent the wave function in the solid, this is probably tractable. There are certainly codes that do it. We typically are using this sort of 3D B-spline representation, and now you have many thousands of coefficients that you would have to optimize for each orbital, and then you might have to worry about something like a normalization, some constraint. So this isn't particularly feasible right now. The only method that we currently have that is generally applicable is a backflow transformation. So I think Miguel talked about this a bit yesterday, where basically you can say that you pick some quasi-particle coordinate due to the proximity of other electrons, and then you can move the nodal surface in that way. Now, unfortunately, unless the cutoff is really small, so unless you're only considering particles that are very close by, it gets very expensive to do backflow for calculations of large solids. So it's also not used a lot. Another thing that you might want to do is calculate a band structure. This is something that's commonplace in DFT. So this would require calculating energies of excited states, let's say, of the system. Now, one thing that you can do is just use the fixed node approximation to your benefit. So if you have something that's orthogonal to the ground state, which you would if you promoted, say, an electron from a conduction to a valence band, or a valence to a conduction band, then you can just run diffusion Monte Carlo, and you'll get some estimate of that energy. Now, in general, we think that we do a poorer job on having a nodal surface for the excited states than we do for the ground state. So you typically think that this is going to overestimate your excitations, your excitation energy. You can do another thing by the extended Koopman's theorem. So there's a way to look at the density matrix of the system so that you can imagine promoting an electron, promoting one state to the valence without relaxing all of the other states in your system. And this has been done in the late 90s. And then another possibility is something like correlation function Monte Carlo, where you look at how various calculated properties evolve with projection. So there are a few references, and then I guess any catch-all questions, and then the second half of the lecture I'll talk about practical calculations that have been done. In the first part of the lecture, I've been talking mainly about the theory of how all of this works. In the second half, I'd like to talk about, in practice, how these calculations have worked for me in solids and the pitfalls that you have to worry about. In practice, as sort of we've seen, there are a variety of approximations that you're going to be making whenever you do a calculation in a solid that you wouldn't have if you were going to do a calculation of a molecule. Most of them can be made arbitrarily small, but they're not standardized. So we've got to look at things like how we're going to do our calculation of one-body finite size effects. How many twists am I doing? Am I comparing to DFT? For two-body finite size effects, we've got 3 or 4 different methods at least of estimating them. How we deal with the fixed node error. So in practice, we generally just live with it for a solid state calculation, but there are other things that one could do. And then how do we construct our pseudopotentials? So if your bottom line question should be, I think, how accurate is this method to apply to systems that I care about? You're going to have to confront all of these issues. And it's unclear exactly what the size of the errors are going to be. So as a case study, there's a fairly recent paper, and quite a few different groups have looked at calculating the phase transition pressure for silicon under pressure. So basically you take typical diamond structured silicon, you put it in a diamond anvil cell and squish it. At some point the symmetry is going to change from this diamond structure to a phase that's similar to beta 10. So what people do is they've calculated the energy, again using all of these methods to estimate finite size effects and so on and so forth, versus volume for the diamond phase and for the beta 10 phase. And they calculate the transition pressure and compare it to experiment. So over in this chart, you can see we've got comparisons. Here's the experimental number that's sort of 10 to 12. So these 4 lines here are quantum Monte Carlo methods of one flavor or another. These 3 correspond to diffusion Monte Carlo, just with different kind of ways of treating, let's say, the finite size effects. And then auxiliary field is another projector method. And you can see that the transition pressures that they're getting vary a fair amount. So some sort of 14.5 to 16.5 or 12 for the auxiliary field, and they're all too high compared to experiment.
Do you think the experiment is that reliable or not? Do you know, has there been any recent work?
Recent work on the experiment.
Because already it says 10 to 13 or something, and I know that there were a lot of questions about whether that was the true thermodynamic phase transition or just hysteretic kind of thing.
I don't know if the worry is so much about hysteresis. People have worried certainly about non-hydrostatic stress. I mean, because you're in a diamond anvil cell and you squish in one direction, and then you have some pressure transmitting media that hopefully keeps it hydrostatic. I mean, the reason that it's 10 to 12 is that there are different groups that have gotten different numbers, and 12 is sort of the highest.
Is calculating this observable have the same variational principle for this pressure?
So
the lower is better?
So I guess I should take a step back. I didn't explain how the transition pressure is calculated. So basically you calculate your energy versus volume curves, and this is variational. And then if you want to know the transition pressure, you need to know the enthalpy at which they're equal, right? So you can do a Gibbs construction, which is basically draw a common tangent to these 2 curves, and the slope of that curve will give you the transition pressure. So lower is not necessarily better. It's not variational at all. I guess in general, if you have different errors, different magnitudes of errors for the 2 phases, that's going to steepen your line. So if you're doing better for for diamond phase or then beta, oh no, I guess it depends on which phase, right? So it can go either direction. If you do better on beta 10, you lower the pressure. If you do better on diamond, you raise it.
The general rule that I think I said on Monday was simpler gives you less bias than more complicated. So we'd have to ask whether beta 10 or diamond are a simpler structure or more symmetries.
Well, there's another issue in that diamond is an insulator and beta 10 is a metal. So for instance, most of these groups aren't twist averaging very carefully in the metal. So you could imagine that there's an error due to that.
But actually you could study, for example, how much correlation energy your variational wave function gives in the 2 phases per atom.
Sure.
As a measure of the quality of your wave function for the 2 phases. That would be actually interesting, because that way it would tell you, I think what he's kind of asking is the bias is favoring lower pressures or higher pressures.
And we don't know.
Except for the experiment, but we want this to be independent of the experiment. So
now generally the auxiliary field people have thought has less of a fixed node error, right? And the fact that it's getting a lower transition pressure might suggest something about how those are treated.
But we'd really like our method not to have to rely on other things, the experiment or other methods.
Absolutely.
If you didn't know a priori that it's beta 10 is the other phase, do you think you would have been able to predict the pressure transition to a new phase?
So given a phase, given asymmetry, you can do the calculations. There's a whole industry. So if everyone didn't hear, the question was basically if I didn't know it was transforming to beta 10, would I be able to calculate the transition pressure? So one of the inputs of the calculation is the positions of the atoms. Now there's a whole industry going on right now in density functional theory of structure prediction under pressure. Right now I would say it's too expensive to do in Quantum Monte Carlo.
Really?
Well,
I mean,
you'll...
I mean, we do this, you know, with hydrogen is you come up with 10 DFT structures, and then, I mean, use DFT to filter out and give you some good candidates.
Right, so you can
And
certainly
then
do
you
that.
run QMC on those as a final determination. I mean, that's possible now, right?
Exactly. Once you have a list of candidate structures, then you can evaluate them in Quantum Monte Carlo.
But that's all DFT does, and I mean, it just makes a random sampling of structures, and so it's going to give you a list, and you believe that it's going to be accurate to 1 EV or something, right? And
sure.
So you may say, well, I only want 10 structures. If you do that, then you may miss something. But with parallel computers, you could look at 1,000 structures, right?
In principle,
Yeah.
sure. So one of the things that I thought when I saw this data is it would be nice to know some measure across more than just one material, right? So each of those groups has made different choices into how they're going to treat the finite size effects, how they're doing their extrapolations. So if we did the same procedure across a wide variety of materials, would we know something more about how the procedure works than about how it happens to compare to a particular experiment? So if you're going to construct this, the test should be something that we can easily compare to measured experimental data. I mean, that's more or less what we have in the case that we can't, let's say, arbitrarily improve our wave function. For my particular application, it's nice that I can do calculations at high pressures and get an observable at the ambient phase. So what I'm going to be doing here is calculating the equilibrium lattice constant and bulk modulus, which are things you can observe sitting on your desk, but the calculations are of things at high pressure. This can get incredibly expensive. So it used to be that if you were going to do energy versus volume of a single solid phase, this was probably going to be your computer allocation for the year on an NSF machine. So one thing that we do is if we only compare within a single phase, then we just have to worry about relative convergence of things like finite size effects, not absolute convergence. And then finally, I happen to have access at that time to a fairly large computer. So the particular procedure that I used first with the pseudopotential is I constructed pseudopotentials within LDA, so within a given choice of density functional with opium. And I compared the results to all electron calculations on those same pseudopotentials. So again, with the local density approximation. Now, there's no reason necessarily to believe that this is going to give you the best Quantum Monte Carlo pseudopotential. That's true. However, there are papers in the literature that have basically said, okay, I've done my calculation with Quantum Monte Carlo. Now I realize that I didn't have very good underlying pseudopotentials, so I'll compare it to all electron with the same method and calculate the difference. In this case, that will be 0. Right, so the bulk modulus and equilibrium volume are nearly the same for the all electron and the pseudo wave functions. In terms of converging the technical parameters, I was really careful about performing calculations for a moderate-sized supercell, but then converging everything really precisely. So here, for instance, is the grid that I've chosen for the B-spline. I can look at how the energy in the variational Monte Carlo converges with that, or the variance of the local energy. Now, something that's been pointed out for these purely periodic solids, you can basically beat this to death. There's not a big worry about the size of memory, so I could have just started over here with a really fine mesh. And then you also do have to be careful about doing this at different volumes, because you could have different errors at high pressure than at low pressure.
What is the B-spline factor as opposed to the B-spline spacing?
So it's the same thing. So the B-spline factor, you've got some distance that's set by the plane wave cutoff, let's say the mesh from your DFT calculation. And the B-spline factor is that number times that spacing in the linear direction. So a factor of 1 is
more accurate on the graph.
1 is more accurate.
Oh.
Right. So I'm decreasing here or increasing the space between the points. So time step convergence with these sort of pseudopotentials and the elements that I did was typically very, very easy to do. So this was something about doing the calculations within a single phase where I don't have to absolutely converge the finite size effects. So I showed this figure before about the energy as a function of the number of twist angles that I did in my calculation. And this would be a similar story in DFT, right? Unless you do some sort of smearing, the convergence with twist is, with K-points is very arbitrary and very slow. But if you look at two different pressures and you compare the energies, you basically take the point where the difference going from one set of twists to the other is the same within whatever tolerance you specify.
There is a procedure to improve this, and that's just simply to do it within DFT and add the correction, and then that would converge faster in twist angle, right? For a perfect crystal.
It does.
Yeah.
Well, assuming the DFT is doing a good job.
Yeah.
Yeah.
But you can check that internally, sort of, right?
Yeah. In fact, the scripts that I was using did that. So that was another thing that was looked at. So once you do all this very carefully, what I'd come out with was a test set of 14 or so different solids, ranging from ionic solids like lithium chloride to things like diamond that were covalently bonded, metals, and van der Waals. And then I would compare the equilibrium lattice constant and bulk modulus to experiment. Now the lattice constants were coming in pretty good to within about 1%. And it's sort of, I would pitch it as saying this is a starting point. So the approximations that I've done using a single Slater Jastrow, for instance, aren't the best thing that we can imagine throwing at this. But it's a place to start in terms of improving your method. You can do a couple of these and see if you're doing better for multiple systems at once. The bulk modulus was similarly quite good. Now the interesting question in terms of are we ready to apply diffusion Monte Carlo to a bunch of solids, I think, is comparing to the performance of the available density functionals. So here I'm showing the percent error in the calculated equilibrium volume of sort of a host of density functionals on the same materials. And the thing that you see pretty quickly is that sort of the hybrid functionals or the second generation GGAs are doing quite well and about as well as the Monte Carlo calculations did for these sort of typical interactions, the metallic, the covalent bonding. However, over here for the van der Waals solids, I also did the noble gases, you don't get very good accuracy. So if you don't know ahead of time exactly what sort of interactions you've got, you potentially have a problem. Now, the other side point is that some of these van der Waals functionals are actually getting quite good. Now, both of the functionals that I choose did pretty well for the noble gases, but sort of one of the more recent ones also has pretty good performance for the rest of the solids. So that was kind of encouraging from a functional development, and to say that the sort of naive diffusion Monte Carlo was at least as good as these across. The next logical question, okay, I did a careful job of controlling the one-body finite size effects, and there was this question about silicon. Is the beta 10 phase, is the error largely due to the fact it's a metal and we might not be doing that well? So I calculated the diamond to beta 10 phase transition pressure with this procedure, and I found that my equilibrium properties were actually worse than reported by other groups. I was off by a couple of percent in equilibrium density and 5% in the bulk modulus, and that resulted in a phase transition pressure that was even larger than what other people had found. So this was a little bit discouraging, but sort of also spurred me to try to do better. So I took a step back from silicon and said, okay, I'm worried about my pseudopotentials. Let's go to something where maybe I can do something about that. So I looked at beryllium. Now it's a light element. I will be able to do all electron calculations on it. However, quantities you might want to calculate are rather sensitive. So there's an equivalent thing you can do in calculating the phase transition between the first two known solid phases. And you can see that the energy versus volume curves, say within LDA, are right on top of one another. So any error that I make in the calculation of one phase versus another will have a huge effect in terms of the phase transition pressure that I calculate. So just to sort of drive that home, I've applied an arbitrary shift to the HCP energy in this curve. So if I arbitrarily say that I estimated the energy of the HCP off by a little bit, what does that do to my transition pressure? So down here is the error in the energy in millivolts. I guess you turn on its head and it's a shift to HCP. And then the phase transition pressure, the scale here is megabars. So this is hundreds of gigapascals. So you can see for a fairly small shift in terms of total energy, well below what people describe as chemical accuracy, you can shift by hundreds of gigapascals. So again, if you apply the sort of procedure that I used for the test set of solids to this, you have to be a little bit careful in that now you're optimizing the C over A for an HCP phase. But okay, you can do this by doing more calculations. You get some C over A that's in pretty good agreement with the experiment. You get an equilibrium volume that's too low, so the density is too high, and the bulk modulus is too high. And the result is that you get a phase transition pressure that's really, really high. Now there is no experimental evidence for this phase transition. It's at too high of a pressure for any of the techniques that we have to measure, but the DFT functionals kind of cluster around 400 GPa. So it's certainly some cause of concern, especially in light of the errors in the ambient phase. Now, if I do an all-electron calculation, so the way that I did this was I built a new pseudopotential that had all 4 electrons in the valence and was very hard. So it looks like a Coulomb potential to fairly small radius and then changes. I did my DFT calculation, and then when I went to do the Quantum Monte Carlo, I just replaced it with 4 over R. So I had a bare Coulomb interaction. The thing you have to be careful about in that sense is now I've got a cusp, or I should have a cusp in my wave function that's not there to cancel out the divergence of the Coulomb potential. So you can put in a one-body Jastrow factor on top of everything to fix that cusp. And you just need to be very careful about your time step, right? So it's possible that you'll have a large error in the wave function in this region, and that'll make your time step have to be infinitely small. So it turns out that that wasn't the case here. And when I do the calculations, I find that the all-electron results are now agreeing with the experiment within a pretty small error bar. So at least for the case of beryllium, it really was the construction of the pseudopotential that I was using for the HTP phase that had almost all of the error in it, as these are still single Slater Jastrow. The question is, now what if I think about revising this pseudopotential generation scheme? I can't continue to do all-electron calculations for platinum, right? So the first thing that I attempted was to still require that the pseudopotentials within DFT were good pseudopotentials. So if I compare to all electron, I get the same results. The thing that I worked pretty hard on is attempting to reduce the locality error in the potentials. So basically, if you stare at it long enough and you work hard, you can make the non-local channels look very similar to the local channels, and that'll reduce the locality error that you have. So you're preserving a Kleinman Bylander form, but you're allowing a change also of a local channel for diffusion Monte Carlo. So for example, in platinum, it may be that your DFT calculation with an S channel looks, as local looks pretty good, but you've got 10 electrons in D. So some small change in that potential to the S1 will result in a very large locality approximation when I do Quantum Monte Carlo. Now in the limit, I have enough projectors in my pseudopotential. It shouldn't really matter which one I choose in the limit of an exact wave function for Quantum Monte Carlo. So that's why we just, in the case of platinum, let's say we would pick D as local. Now for platinum, because that's something I've been working on, if you calculate the energy versus volume for the solid, you're now finding pretty good agreement with experiment, right? So within a few percent, and the bulk modulus looks pretty good, and the binding energy looks pretty good. So at this point, I was very happy, and I said, okay, I'm going to apply this to another material. Things looked reasonably good for platinum, which was a fairly heavy element to do in Quantum Monte Carlo. So I wanted to apply the same procedure to another heavy element, and so I chose silver. And in this case, you get the elastic properties, things like the stiffness of the material. The bulk modulus is quite good. The ambient density is off by 7%, which is kind of an unacceptable error. And then you can see that the cohesive energy is also off by quite a lot. Now, one thing that was encouraging is all of this effort to reduce the non-local channel in the pseudopotential did pay off, and that the variance of the DMC local energy and the time step that I needed to get a small time step error were very small. So the wave function was actually fairly well adapted to the pseudopotential that I used. It's just the Hamiltonian that I solved was the wrong one for silver. So one thing to look at going forward, of course, is the choice of core valence separation for silver. And this is going to be the case for a lot of the heavier elements that we'd like to work with. And one of the potential issues with some of the pseudopotential sets out there, like the trail needs, is that you might imagine that in this case, there's a fairly strong overlap between some of these semi-core states and the valence states. So in energy, they're separated by quite a lot, but spatially they aren't. So putting these semi-core states into the valence might have a beneficial effect. So and the last thing to say is that what I had primarily worked on was sort of methods outside of how do I choose a good pseudopotential. But there's another way to look at the problem, and that is, okay, given a pseudopotential, how can I test it and see whether this is a good pseudopotential? Now, clearly, calculating an energy versus volume curve is a very expensive way to go about that. That's millions of CPU hours, typically. So you come to something like what I consider to be a very highly successful application in this recent paper from the Oak Ridge group, where they did just what you did in your lab, which is calculate ionization potential and electron affinity of the isolated atoms. You calculate binding curve of some dimers of interest, and then you compare those results to experiment. There's more to be said on this story. I think there are going to be more pseudopotentials coming out, and I'm actually fairly excited about this. So does anyone have any more questions about how to apply QMC to solids? Yes?
Some of the nice van der Waals pseudopotentials, are they not usable in Quantum Monte Carlo because of all the reasons that you've been told that pseudopotentials aren't usable?
Sorry, what do you mean by a van der Waals pseudopotential?
You were comparing the DMC results to different DFT results using with what I think was different pseudopotentials, including some van der Waals pseudopotentials, and those did very well.
Right.
Could you use those to make your wave function much better?
So in that case, they were actually PAWs that were used. So in DFT, there's this method of basically having a mapping between your valence problem and the full all-electron problem that turns out to be a very accurate way to do the core valence separation. So unfortunately, there doesn't seem to be an easy way forward to use that.
For your test set of all the solid, do you have the expectation of the cohesive energy?
The cohesive energies?
Yeah. Do they follow the same chain?
So I do know that there are some groups that are working on kind of test sets of cohesive energies. I shied away from it at the time for a couple of reasons. One is that my finite size effects, as I mentioned, weren't necessarily completely converged in an absolute sense, only relatively within the phase. So that would be a more expensive thing to do. The other is that in general, I worry that I can calculate the properties of an atom much more accurately than I can calculate the properties of a solid, right? I could do one of these quantum chemistry sort of expansions and get a very, very large fraction of the correlation energy, whereas in the solid, I wouldn't be able to improve the wave function as much. So if you did that, you would expect to underestimate the cohesive energy across things. So I've sort of been waiting until I can get a better procedure for the solid to attempt that comparison. But it's a good idea for the test, I agree.
In your experience with the outlier generator pseudopotential, if the optimized pseudopotential scheme will be always better than the 3 and pseudopotential, or depend on the case?
Unfortunately, it does really seem to depend on the case as to whether the extra freedom of that optimized method versus Trier-Martin's or the Kircher method really gave you a better pseudopotential. So.
Another comment, there is a lot of room for possible improvement in the pseudopotential. So we have things at work, but there is room for improvement. So if any of you wants to learn the field, it's certainly a place to publish papers, but it's not easy.
And I'll say it's actually somewhat in contrast to the experience with the quantum chemistry sorts of things. So for calculations on molecules, it seems like the quantum chemistry pseudopotentials are doing quite well, whereas we haven't had the same sort of success even applying the same potentials to condensed matter in all cases.
How will they differ? I mean, it's because they're based on DFT?
So I think some of it is they're based on DFT. Some of it is the issue of projectors. So an interesting thing to do would be to calculate semi-local wave functions and apply them.
You mentioned that the AF QMC seems to work better. Are they using the same pseudopotentials?
So auxiliary field can use whatever pseudopotentials they like,
So
since they're just running
when
matrix
they did
elements.
the silicon calculation.
They were using an opium-generated pseudopotential, whereas actually the...
Then how could it be that if you're using the same pseudopotential, that it couldn't be the problem with the pseudopotential then?
They weren't using the same opium-generated pseudopotential that I was. I didn't have that.
Opium one.
One certainly could.